Hi, welcome to Chapter 11, Overview Part 1, where we're going to talk about solids, liquids, and gases, and intermolecular forces. So what is the intermolecular force? So first of all, there's an intramolecular force, where there's an A here, and an intermolecular force. And what is the difference between them? Well, an intramolecular force is a fancy name for bonds. Okay, so you see in this picture they're showing you right here is the intramolecular force. So that could be covalent, ionic, or metallic. Okay, that's your bonds. These are very strong. Now your inter means between two molecules. So this is your intermolecular force right here, okay? That is what holds molecules, i.e. two or more together. Okay, so how do they differ in strength? Well, I already said intra is very strong. It's a bond. Very hard to break. Inter is not quite as strong. So the attractions between molecules are not nearly as strong as the intramolecular attractions, which are your bonds that hold the compounds together. Why are intermolecular forces important? Well, they dictate many physical properties like the boiling temperature, the freezing temperature, melting point, viscosity, surface tension, capillary action. All of these depend on the forces that hold more than one molecule together. And in particular, they also predict what state of matter you'll have at certain temperatures. So let's talk about the three states of matter: gases, liquids, and solids. Gases, you have no volume, where they actually take the volume of container, so they completely fill it. And they take the shape too. So they take the volume. Actually, let me just erase all that. They take volume and shape of the container because they do not have their own. Okay? Totally disordered. Particles are far apart. There's no order to them, moving rapidly. Okay? Then you get to your liquid where the particles are closer together. They have volume, but no shape. Then you get to your solid where there is a repeatable pattern. They have shape and volume. In your solids, because the particles are so close together, this is where your intermolecular forces are the strongest. So what determines the state of matter a substance will be in? Well, there's two factors. One, the kinetic energy of the particles. Remember, that's related to temperature. And two, the strength of attractions between the particles. So that depends on your intermolecular forces, which we're going to call IMFs, okay? Also, you should know that solids and liquids are referred to as condensed phases because if you go from a gas to a liquid, you have to condense it. And then if you go from a liquid to a solid, you have to condense it even more. You're bringing the particles closer together. So the fundamental difference between the states of matter is the strength of its intermolecular forces. Okay? The stronger the forces are, it'll bring the molecules closer together. Okay, leading you towards the side of a solid, away from a gas. The kinetic energy, these are like two competing forces. You have your intermolecular forces, which are pulling your particles together, but then you have your kinetic energy, which is pulling them apart because they are moving. So that is why your temperature will really help you dictate what state of matter you're going to be in. Okay, and here's a zoom in. Here you see your gases are far apart. Here your liquids closer together. Solids very close together. So the relative strength of attractions. You could kind of tell how strong the attractions are by looking at the melting and boiling points. Okay, the higher the boiling point, the stronger the attractions. Okay, so intermolecular attractions are weaker than bonds. And one of the intermolecular forces, which we're going to talk about a little bit more later, is called hydrogen bonds, but that is not a bond. So I always like to do this. Not a bond. It's an intermolecular force. So sometimes these intermolecular forces are also called interparticle attractions, or IPAs. And there are 6 main different interparticle attractions. One where you have an ion and a polar molecule. That's called ion-dipole. So the positive side, if you have a positive ion, that'll be attracted to the negative side of your polar molecule. Then you have something called ion-induced. That's when you have an ion that comes close to a nonpolar molecule and it forces that nonpolar molecule to get an instantaneous dipole. And then they'll be attracted to each other. Then you have hydrogen bonds, which remember are not bonds, so we're going to do that. Where you have 2 polar molecules where hydrogen is bonded to oxygen, nitrogen, or fluorine. Then you have dipole-dipole, where you have 2 polar molecules that are attracted to each other. Or you could have dipole-induced polar, where you have a polar molecule that comes near a nonpolar molecule, which then forces this to get an instantaneous or an induced dipole, and then they'll stick together. And the last one is dispersion, which is present in all molecules. All molecules have dispersion. And it's the only force between 2 nonpolar molecules. Dispersion can also be called London dispersion or induced dipole. This is a lot to say, so we just go with dispersion most of the time. So the types of intermolecular forces between neutral molecules. Okay, so here we have dispersion forces, which are also called London dispersions or induced dipole interactions. And then you have dipole-dipole, and then you have hydrogen bonding, which is a special type of dipole-dipole. I always like to say it's a dipole-dipole on steroids. Note the first 2 here are known as van der Waals forces. Remember his equation from last chapter. So let's talk about dispersion forces, which are present between all molecules. So let's first look at a nonpolar helium. So here you have nonpolar helium. Your electrons are on opposite sides of the atom. There's no attractions really, and it's really not polarized. It's just sitting there, okay? But there is a probability that these 2 electrons would be on one side of the atom. And at that instant, they'll have a dipole. And then if another helium atom came close to it at that instant, it can induce a dipole in that helium. And then they would be attracted to each other. Okay? When they do that, you are distorting the electron cloud. And the ability to distort the electron cloud is called polarizability. Okay? So let's kind of step through this. So here we have our helium, where there is a probability where the 2 electrons will be on one side, okay? This is because the electrons are moving, and in any split second of time, you might have this happen. Okay, so when the electrons in a 1s orbital of helium, they normally would repel each other and therefore tend to stay far away from each other. But it does happen that occasionally they will wind up on the same side of the atom. When that happens, they form a dipole, and this is how we're going to represent our dipoles. Well, remember, this means partial negative, and this is partial positive. So this is negative over here because the electrons are over here, and this side is positive because the electrons are missing. Okay, remember when we draw our dipole, we use an arrow, where this is on the positive side, and the arrow points to where the electrons are spending most of their time. So at this instantaneous moment in time, helium is polar. What happens if another helium is nearby? Then, if it came close to it, they would have a dipole induced in it. Because the side is mostly positive, the electrons are going to want to come over here. So you're going to induce a dipole in the second helium. And then at that instant, these two heliums will be attracted to each other. Okay, and this is how we're showing it here. So another helium nearby then would have a dipole induced in it, and as the electrons on the left side of the helium of atom 2 repel the electrons in the cloud of helium 1, so it's going to push them away, so then you're going to have this electrostatic attraction here, which is called London dispersion. London dispersion forces or dispersion forces are attractions between an instantaneous dipole and an induced. So the instantaneous one was when these two electrons just happen to be here. When they come close to this atom, they're going to force those electrons away and they're going to induce a dipole. These forces are present in all molecules, whether they are polar or nonpolar, it doesn't matter. The tendency of an electron cloud to be able to do this or get distorted is called polarizability. So what factors affect London dispersion? So let's look here at this table. The strength of the dispersion forces tend to increase with an increase in molecular weight. Look at here. As we're going down, the molecular weight is getting greater, and what's happening to my boiling point? It is increasing. It is increasing because my intermolecular forces are increasing, because my London dispersion forces are increasing, because all of these are nonpolar. And if you remember, fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. As you're going down, your London dispersion forces are getting stronger, so you're actually changing your state of matter. Large atoms have large electron clouds, which are easier to polarize. So the easier it is for your electron cloud to polarize, the stronger your dispersion forces. Same thing here with the noble gases. You see, as the molecular weights are getting greater, your boiling point is increasing. So stronger dispersion forces, higher boiling points. So let's look at something else that affects your London forces. So here you have two molecules. This one here is called N-pentane, and it's kind of long. And this one here is more grouped up like a ball, and it's called neopentane. So N-pentane and neopentane are isomers of each other. N-pentane, the one on the top, boils at 309.4 Kelvin. And neopentane boils at 292.7 Kelvin. Why would this occur? When they both, since they're isomers of each other, they both have the same molar mass. So what affects your dispersion forces? The number of electrons in the atom. So the more electrons you have, the more dispersion forces, okay? The size of your atom or molecule, the larger your molecule, the stronger the dispersion forces. And the shape of your molecule, okay? So if you have two molecules that have similar masses, like these two do, the shape of it comes into play. The more compact, the less your dispersion forces. So here we are more compact, and we have less dispersion forces. Okay, so the shape of the molecule affects the strength of dispersion forces. Long, skinny molecules, so this is long, skinny, will have stronger London dispersion. And this is due to the surface area. You have more surface area where you can affect that electron cloud and induce a dipole. So more area here where you could kind of get the electrons to move around more and induce a dipole. So this has stronger intermolecular forces, which is why its boiling point is higher, even though their molar masses are the same. So let's talk about when we have polar molecules. When we have two polar molecules, they have something called dipoles. So here is your polar molecule. One side of it is partially positive, the other side is partially negative. And they are going to attract another molecule, you know, to its negative side, the positive side. And those attractions are called your dipole-dipole interactions. Okay? So in this diagram, the red lines are your dipole-dipole interactions. The blue lines are repulsions. So molecules that have permanent dipoles are attracted to each other. The positive end of one molecule is attracted to the negative end of the other molecule. These forces are important when molecules are close to each other. So for dipole interactions to occur, you need to be close to each other. Here's another picture of dipole-dipole interactions. Okay, so polar molecules have a more positive and a more negative side. They have two poles, the partial positive and the partial negative. So here you see this side is partial positive and this side is partial negative. The partial negative is going to be attracted to the partial positive, and that is your dipole-dipole interactions. The red dotted lines are your dipole-dipole. If for some reason your two negative sides come close to each other, they're going to repel each other. The opposite ends attract each other. Opposites attract. So dipole-dipole interactions. So let's look at our data table here. All these molecular weights are similar, but look at our dipole moment, okay? The dipole moment, if you remember correctly, is the arrow that we draw, right? Going from our positive end to our negative end. If the electronegativity differences between our two elements is very large, it has a high dipole moment. So, a high dipole results from large electronegativity differences. Now notice, as our dipole increases here, our dipole moment, what is happening to our boiling point? It is increasing. So now let's just take a step back and remember, what is electronegativity? The ability to attract an electron. So if we have two elements that have a large electronegativity difference, that means the electron is actually spending more time around one element than the other. So the larger that difference, the more time it's spending around one element, not the other. Thus making that partial charge on the molecule a little bit more negative on the negative side, a little bit more positive on the positive side. So the attraction between the two molecules will be greater, which is why the boiling point is higher. So here you see here, again, they all have very similar molar masses or molecular weights. But as we go to the right, they are becoming more polar. And as they become more polar, the boiling point increases. So for molecules of approximately equal masses, and that's important, equal masses and sizes, so if that is the same, then you could actually compare polarity. So the more polar the molecule, the higher its boiling point. So which has a greater effect, dipole-dipole interactions or dispersion forces? Well, if two molecules are the same size and shape, then the dipole-dipole interactions will dominate. But if you have one molecule that is much larger than the other, then dispersion forces will dominate. Okay, so again, let's say that again. If you have two molecules that have the same size and shape, then dipole-dipole dominates. But if you have two different size molecules, the larger one will have greater dispersion forces, and the dispersion forces will dominate. So let's look at this graph here. So here we have our molecular weight versus boiling point. So if you look at group 4A, as the molecular weight goes up, the boiling point goes up. Because as the molecular weight increases, your dispersion forces increase, so the boiling point increases. Okay? As molecular weight increases, dispersion forces increase, so boiling point goes up. But we have these anomalies right here. These are much higher than everything else. What is going on with those three molecules? Everything else here follows. It's increasing, increasing, increasing. So what is happening with period 2 elements? Well, we have something called hydrogen bonding. So hydrogen bonding is a dipole-dipole interaction when hydrogen is bonded to nitrogen, oxygen, and fluorine. And why these three elements? Because they are the most electronegative elements on the periodic table. So now you have an extremely polar dipole. Okay? We call these interactions hydrogen bonds, but remember they're not bonds, they're intermolecular forces. So if you look here, here's your water molecule, and oxygen, which is partially negative, is attracted to the partially positive side of the other water molecule. This here is your hydrogen bond. In order to have that, you have to have hydrogen and oxygen bonded to each other, which we have right here. And hydrogen and oxygen bonded to each other. Here we have hydrogen bonded to fluorine, hydrogen bonded to fluorine. The attraction here, because this is negative and this is positive, is the hydrogen bond. Here we have hydrogen bonded to nitrogen. So this is your negative, this is your positive, that's your hydrogen bond. They will even hydrogen bond to each other, as long as hydrogen is bonded to oxygen, nitrogen, or fluorine. What forms hydrogen bonds? Hydrogen bonds arise in part from highly electronegative nitrogen, oxygen, and fluorine. Again, those are the three most electronegative elements on the periodic table. These atoms interact with a nearly bare hydrogen nucleus because it only has one proton and one electron. There are no inner electrons. So you see here, your electron is going to spend a lot of time around your electronegative element. I always kind of like to illustrate it kind of like this. Where imagine your electron traveling. It's spending most of its time here, so it is negative a lot of the time, maybe 90% of the time. So that's why you get a very strong dipole. And that's why they're attracted to each other so strongly. And hydrogen bonding is very important, especially in water. Okay, hydrogen bonding makes the water molecules further apart in ice than in water. So they form this hexagon, this honeycomb structure. And this is why ice is less dense than water. Because this is all empty space here. Empty space. This is ice. Okay, because of the hydrogen bonds, which are the dotted lines here, these water molecules can't get closer to each other. So when they freeze, you have a lot of empty space, and ice turns to expand. If you ever put a bottle in the freezer and then you go back open the freezer, the bottle might crack because the ice expands. Okay, the last interaction we're going to talk about is ion dipole. And this is how we get ionic compounds to dissolve in water. So you have your ion, chlorine, and you have your polar molecule, so the positive side of the water is going to surround the negative side of the chlorine. The strength of these forces, they are very attracted to each other, is what makes it possible for ionic substances to dissolve in polar solvents. So how do you determine the intermolecular forces in a substance? Okay, so if you just have atoms, they're going to have dispersion forces. They don't really have any charges on them, so that's the only thing that's going to take place. Now notice the range of the energy of these forces. Dispersion forces were always taught were kind of weak, but that is not necessarily true. They have the largest range. They could be very weak to very strong, depending on the size of your atom. If you have nonpolar molecules, dispersion forces are the only thing holding them together. But look, dispersion forces are everywhere. They are in polar molecules, they are in hydrogen-bonded molecules, and they are in ionic solids. So you always have dispersion forces. Let's look at dipole-dipole. Look at its energy ranges from 2 to 15. They are present in polar molecules bonded to each other and when you have hydrogen bonding. So when you have hydrogen bonding, you have both dipole, dipole, and hydrogen bonding occurring. Now let's look at hydrogen bonding. See how much stronger hydrogen bonding is? It goes all the way up to 40. And that is when you have polar molecules that have oxygen bonded to hydrogen, nitrogen, or fluorine. And ion-dipole interactions are only for your ionic solids. The strongest force dictates the extent of attraction between the molecules. The more the molecules are attracted to each other, the stronger the force. So what are some generalizations about the strength of your intermolecular forces? When two molecules have comparable molar masses, that means the same molar masses and size, then your dispersion forces are roughly equal. When two molecules have very different molar masses and there is no hydrogen bonding, dispersion forces will determine the substance with the strongest attraction. So how strong are these forces? Well, London dispersion forces make up more than 80% of the attraction forces in hydrochloric acid. The energies that are associated with these, so dispersion, it could range from 0.1 all the way to 30, so it could be very, very strong. So don't underestimate the dispersion forces. Dipole-dipole can range from 2 to 15, so they could be strong, but dispersion forces could be stronger, especially if your molecule is very large. Hydrogen bonding, we always said, was the strongest of the intermolecular forces, and it could go up to 40. And ion dipole, which is really the strongest, so it's greater than 50 kilojoules per mole. So how do you know what type of intermolecular forces you're going to have? Well, you can follow this flow chart. So you say to yourself, I have two molecules or ions. Are ions evolved? If the answer is no, then you say, are polar molecules evolved? If it says no, then you could only have dispersion forces. If you don't have ions, but there are polar molecules involved, then you have to look and see, is hydrogen bonded to nitrogen, oxygen, or fluorine? If no, then you have dipole-dipole forces and dispersion forces. Remember, dispersion forces are in all of these. If the answer is yes, then you have hydrogen bonding. Up here, if you do have ions involved, are polar molecules and ions both present? If the answer is yes, then you have ion-dipole forces. And if the answer is no, then say you just have two ions, then you're going to have ionic bonding. Okay? These here are your van der Waals forces. So let's try to describe what type of intermolecular forces are occurring between two hydrochloric. So this is polar, and that's the dipole, so it is polar. So between two polar molecules is going to be dipole-dipole. Water molecules are polar, and we have hydrogen bonded to oxygen, so this is going to be hydrogen bonding. Two nonpolar, this is going to be dispersion. See this OH tail here? That tells you it's hydrogen bonding. Now, what is important to note, dispersion is present everywhere. And that is the end of part 1.